Study of motion. What is a revolution? Okay, it's not just a full turn. It's a full turn around a what? For something to revolve, spin it, it has to have an axis. Yep. It is the circular motion of an object about an axis. Roller coaster going around a loop. Earth orbiting the sun. Notice it's not about a central axis. It's an axis that is not inside the object. Bog on the edge of a record player going around. Okay? That's different than rotation. Rotation is spinning of an object when the axis is inside. Yes. So this is still circular motion, but it's about an internal axis. A wheel spinning, the earth spinning around its axis. Okay? The record itself going around on the turntable. A basketball on the end of your finger, spinning like you're a Harlem Globetrotter. All right? Here's the problem. When we get to angular motion, circular motion, we're talking about angular stuff. Because when we talk about motion and going around in a circle, we're no longer talking about a straight line in meters anymore, are we? What we're talking about is 360 degrees. That's angular, isn't it? So when we talk about this, we talk about something going around 360 degrees or some portion of 360 degrees, okay? Now, kinematics can be done in a rotational format. We can actually equate linear and rotational stuff, okay? In other words, we can take the part of the loop and we can lay it out straight. We have a way of doing that if we need to. So let's talk about what's going on here. At time 0, we know our object is starting here in relation to the center, okay? After some time t, it is now gone from here, traveled around some distance, and gone to here. This represents some angle that it is gone, right? Well, that angle also represents some distance along the edge of the circle that it is gone. Well, guys, that's an arc length, isn't it? Remember geometry? You talk about the edge of the circle. This is an arc length. And we can talk about what that arc length is. So the units of angular displacement are either degrees or what we call radians. All right? And remember, 360 degrees is equal to 2 pi radians, right? Remember that from math class. Unit circle. You are correct. Unit circle. All right. So what is the relationship between linear distance and angular displacement? It's the length of the arc. Okay? It is the length of the arc, and what we get is if we call this S, and we know it is some radius r, and this is some degree theta, that the length s is equal to the radius times the degree it went around.
I need coffee.
Please come through and get coffee. Elf needs coffee badly.
Oh. What are we doing here?
Linear distance and angular displacement.
Angular displacement.
What's a real-world example of angular displacement?
How far your tire goes around in one rotation?
That's excellent. All right. Go kick butt. Don't hit anybody.
That's right.
What's on real quick?
4:30.
I'm recording this.
Go
I'll
here.
post it.
Oh, we're recording it right now?
Oh, it's fine.
Oh, okay.
No problem.
A little extra something for the people.
Oh, please. The things I've said. Shoo. Yep. So he knows. All right, so here goes. We want to look at rotational kinematics today. Now, rotational kinematics does have something to do with horizontal or translational kinematics, right? So far, all we've talked about is one direction or maybe even 2D, but it's all been up and down, side to side. That's translational. Now we're going to talk about what do we do to figure out velocities and accelerations and displacements if we're going in a circle, okay? What is kinematics, guys? It's the study of what? Motion. That's exactly correct. It is the study of motion. Now, you need to understand the difference between a revolution and a rotation. Have you done your service hours?
I'm sorry.
How much do you have done? All right. So we need to know the difference between a revolution and a rotation. Both of them are something turning about an axis, okay? They're both circular motion. So that's what we're studying this unit. Circular motion about an axis. Rotation, still. Circular motion about an axis. But I said there was a difference between the two. Look at the examples of them and see if you can tell me what the difference is. For revolution, your examples are a roller coaster going around a loop, the Earth orbiting the sun, whereas for rotation, it would be a wheel spin, the rotation of the Earth about its own axis. Yeah, what's the difference between the two? Revolution versus rotation. Since we just started and said they were the exact same, something's got to be different.
Well, revolution's like and then rotation's like inside the pin.
Oh,
Yeah,
very
like
close.
Rotation, I always hear it as like a tire, like a wheel, and revolution is usually like a sphere.
Okay, it has to do with this guy right here, where that's located.
Oh.
So you were kind of right. You were on the right track. Rotation, if you think about it, if you've got a wheel spinning about an axis, where is the axis located? Inside, isn't it? And you're talking about the Earth about its own axis. The axis is still inside the object. So it is rotating if the axis is inside. It is revolving if the axis is outside of the object. Okay, so let's talk about kinematic qualities. For every translational quality we had in kinematics, we have an analogous, that means like it, rotational quantity. So what were the big quantities we talked about when we talked about kinematics? I'll start you off. Displacement. What else? Velocity and acceleration. And the last one is time, right? Time. So displacement, velocity, acceleration, and time. Now time doesn't change no matter what you do, does it? So time's going to be the same for both of them. But for displacement, we can have linear displacement or we can have rotational displacement. There's a roll down there, but yes. All right, so let's start. We were talking yesterday about hose in stats class, so. All right, reject and hose. You'll have to take stats if you want to know about reject and hose. All right.
I don't know where my coffee cup
All right. Example A. I'm sorry. Example A. You have a hipster. Whoop, hipster. There you go. Colby. You have a hipster spinning a vinyl copy of an album. That's why we know he's a hipster, because he's got vinyl. You've probably never heard of in their vintage record player. The record spins 10 times. Find the angular displacement of the record in that time. Guys, we know this. S equals R times theta, don't we?
Oh, we do?
Yeah. We don't know R, do we? So we got to figure something out. Okay. But here's the thing. We know that it's going around how many times? 10 times means 10 revolutions, doesn't it? 10 revolutions. All right. All right. One revolution is 360 degrees. Yes. So, guys, this is actually a really easy question if you think about it. Oh, guys, come on. It just wants to know the angular displacement. How many degrees does it go around in one revolution?
360.
How many revolutions does it make?
10.
Yeah.
3600.
360 times 10 is 3,600 degrees, but we like things in radians. Yes, we do. We do things in radians here. So all we have to do is convert to radians. There are 2 pi radians in how many degrees? 360, right? Yeah, we could have. 2 pi times 10, so we end up with what? 20 pi radians. Yes. See, simple, simple. You just got to think about it the right way. All right, so now, while the record's spinning, fly stands on the record 10 centimeters from the center. Find the length of the fly's path while the record is spinning. All right. So do we know how far he went? Do we know his radius? Yes. So can we find his length? This is where our formula comes in.
Does it matter if it's in centimeters at this point?
Yes. It does, doesn't it? Everything has to be in what? Meters. S equals R times theta. So what is R?
Theta over S.
5. What's it?
0.1. Thank you, Emma. 0.1 meters. And what is theta?
25.
Thank you. Didn't we just find that? He went around 10 times, right? So 20 pi. No. You just need to multiply by pi. Can you not multiply that together, guys?
Is that 2 pi?
I want it in meters, though. You gonna tell me the fly went 2 pi meters? What does that even mean?
6.28.
6 point what? Okay. So he actually went 6.28 meters. That certainly makes a lot more sense, doesn't it? Nobody thinks in terms of pi.
He went like 18 feet?
Yeah.
That fly? Oh, he's dead.
He went around 10 times.
No, but the thing is that like a carousel.
Now, here's my question to you. Here's your theoretical question. If the fly is sitting on the outside edge of the record instead,
Fast.
is his angular displacement any different?
Yes.
No.
Angular displacement.
Degrees stay the same. It still goes 1 full circle.
Thank you. Degrees stay the same. It still goes 1 full circle. Is his linear displacement different? Is it going to be bigger or smaller?
Bigger.
Why bigger?
Because the radius is bigger.
Because the radius is bigger. Good. Now we're firing on all cylinders.
Yes, and this fly is going for the ride of his life.
Yes, he is. Now, let's talk about how fast that fly's going. Angular velocity. So rate of angular displacement, how fast an object's spinning. So this is going to be angular displacement divided by time. Doesn't this look a lot like velocity? What was velocity? Change in distance over a change in time, right? It's x over t. But now, instead of x, instead of going in a straight line, what are we doing? We're going in a curved line. Notice that this is no longer v, it is omega. Omega is the Greek letter for angular velocity. Angular velocity is going to be the change in angle over the angular displacement, over the change in time. So this would be like s over t, wouldn't it? No, that's not s. You tell me. S is the linear displacement, isn't it? What was the angular displacement? That was part A. What did we measure angular displacement in? Radians? We still used theta, didn't we? So this is going to be theta over t. What are the units of angular velocity going to be? Theta is in radians, and time is in, so it's radians per second. Now here's the thing. In physics, we don't have really used radians as unit. You're not going to see rad per second. Radians is like invisible. So what you're going to see is it's going to read this. You're going to see it as seconds to the -1. Now, what else have we seen that's seconds to the -1? Hertz. So angular velocity is measured in hertz. Yes, it is. It's hertz.
This hurts.
So angular velocity has a relationship to frequency in simple harmonic motion. I want you to think about why it has frequency in simple time. It's going in a periodic fashion, isn't it? Back to the middle, back to where it began, 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 right? That's a period. So it has a period as well. All right, so now, vector direction. You've got to learn the right-hand rule. Here's the weird thing. It does have linear velocity, guys. It has a linear velocity, but here's the problem. The linear velocity is not in the same direction as this. If it's moving this way, if it is rotating this way, take your right hand. If it is rotating counterclockwise, go counterclockwise with your hand. Counterclockwise. See? If it's going counterclockwise, guess which direction the velocity is going? It's not the direction your thumb is pointing. So it's coming out of the axis. Now, what if it's going clockwise? Now the velocity is going down or into the page. So if we've got this, that's the right-hand rule. Okay, we'll use that again. No, you cannot use the left-hand rule. You could, but you'd have to flip it around.
I remember
Think
this.
about it. Right-hand rule says counterclockwise is up. If you use your left hand to go counterclockwise, which way is your thumb pointing? So if you have to, because of an injury, use the left-hand rule, you're going to have to flip it over. It's going to be opposite of whatever you read,
I've never been more
right?
in my entire life.
All right, so if our bug is going counterclockwise on the edge of this record,
Gosh, is it still
the
the fly?
velocity is coming out the axis, right? Coming out the axis, and it's pointing up. Now, I want you to think about why that would be. It's really hard to picture, but I want you to think about something unscrewing. We spin something really fast, unscrewing. Which way does it unscrew? Up. Righty-tighty, lefty-loosey, right? So if we spin it left, it's going to go up really fast, isn't it? The faster we spin it this way, the more it's going that way, right? And if we want to tighten it down, yeah, righty-tighty, right? Think about it. Going right, Yeah, me. Huh? I think they knew that first. And that's why they invented the screw weight. Yeah. If you spin something this way, anybody ever sew? I sew, and I see this happen all the time. If I sew, and you've got thread on a spool, don't you? You got thread on a spool, and thread is unwinding clockwise. If I have to make sure it's unwinding clockwise, because if it's unwinding clockwise, which way does it really want to, which way is the velocity going? Clockwise, it's going down. Here's the problem. If I flip it over and it's going counterclockwise and I press really fast on the pedal, guess what my spool's going to do? It does. It shoots up off the spool holder. Yeah. That's what happens. So, if you look at a top and a top spinning, a toy top spinning, when you pull it, it spins, it's set to spin clockwise because they want it going, pressing down, don't they? They want to keep it pressing down towards the earth, not up. All right? So everybody understand relationship of velocity versus in the right-hand rule. Do you get right-hand rule? So we've got this vector direction is the right-hand rule, okay? Now, what is the relationship between angular velocity and linear velocity? Linear velocity is equal to this. Angular velocity times r. Think about why that is. Angular velocity is just radians per second, right? Linear velocity is meters per second. So where do we get the meters from? This guy right here, don't we? This is the formula you need to know. Now, look on your formula sheet. Look on your formula sheet. Hang on. Let's look. I don't think it's on there. Nope. You're going to have to know this one. Sometimes. All right. Angular acceleration. Now let's look at angular acceleration. It is the rate of change of angular velocity. Just like regular acceleration was the rate of change of regular velocity, right? Acceleration, look guys, if acceleration is equal to the v over t, then angular acceleration is equal to omega over t. And that's the Greek letter for a. Okay? Do you see that there are relationships here? Every linear kinematics equation has a similar one that covers rotational motion. Only instead of x, we're always going to see what? Theta.
Students,
Theta, the angle.
have been sitting in caught you being great names to Miss Crow. Today's through Monday's names will be drawn for a free general admission ticket to our Black Bear Bash Wednesday at 12:15 in the gym. If your name is called out, please see Miss Crow in the 106 or outside the credit union during second block to pick up your ticket. These tickets are sponsored by Mr. Jason Palmer and State Farm. Teachers, please continue to send in names using the Google form sent by Miss Crow. Keep being awesome, Austin.
Are you going to the
Concert tickets are available for purchase outside the credit union during second block or in the cafeteria A-Hop. Today's random picks are Noah Howard, Osmore Alvarado, Sanaya Smith, Heaven Baggett, Nayeli Gonzalez, Briley Mitchell, Michael Burton, Jackson Gully, Jeremiah Travick, Natalie Adams. Also, if you have already purchased a general admission ticket, it will be exchanged for a VIP. Thank you.
All right. So, units of angular acceleration. Seriously, guys, units of angular acceleration. if acceleration, guys, think about it. If acceleration is meters per second squared, then angular acceleration has got to be radians per squared, which is usually just s to the negative 2. Okay? That would be your units.
I thought S was
Seconds. No. Seconds as a unit, it's s. It's a formula that's for your linear displacement around the circle. All right. So, relationship between linear speed and angular velocity. Think about it. If v was equal to omega times r, then a is equal to alpha times r, right? Yes, it is. Now, what did I say about your kinematics equation? For every linear kinematics equation, there is an equal rotational. And take a look. Here are my linear equations. Now I need to write my rotational ones. Look how easy this will be. Everywhere there's a d, I'm going to put a theta. Theta is equal to, everywhere there's a v, so d is going to be theta. It changes to theta. V changes to omega, and a changes to alpha. This is terribly hard, isn't it?
Wait, what does V change to? What is that?
Omega. Omega. Greek letter omega. A is alpha. So this guy becomes what? Theta equals omega initial t plus 1/2 alpha t squared. Look at that. And this is change in delta because, remember, it's actually, so that would be angular displacement, right? So the angular displacement, so this is angular displacement. Angular displacement is also delta theta. V is omega final times t minus 1/2 alpha t squared. Look at that. So this v becomes omega final squared equals omega initial squared plus 2 times alpha times change in theta. This guy becomes omega final, omega initial, plus alpha t. And then finally, change in the angle, omega initial plus omega final divided by 2 times t. All right, we did not get as far as I'd hoped we would get, but that's okay. We need to do some more examples before I set you loose on homework. So we will do examples next time. Right before you take your test, we'll probably take about 10 minutes and finish up these notes so that you can do your homework after the test. Right now, you need to practice and study for your test. Everybody good? Okay. Homework is just study. We will take the first 10 minutes of class next time before you take your test on Monday, to finish up the examples here, and then you'll take your test. You should have plenty of time still. It's still just 10 multiple choice and 2 free responses.